In the last video, I talked a lot. I got kind of excited. I probably talked too quick. I gave all sorts of theory and really tried to get you to understand the idea behind the derivative, the slope of the tangent line to a curve at a given point. And if you could kind of understand some of the theory and ideas behind this hugely important concept, that's awesome. But if you left that video maybe a little bit confused or a little bit unsatisfied because we didn't actually finish any problems, well, the point of this video is to fix that. In this video, I'm going to be doing all of the calculations. I'm not going to focus on the theory and the ideas behind this. At least I'm going to try not to. And instead, I'm just going to do the work, show you how to get the answers. But hopefully, that work will make sense. It won't be a memorization thing. It'll be more of an understanding thing after watching the previous video. So let's start from the start. Suppose I gave you some function. The equation of that function is x squared minus 4x plus 1. Really, all we're going to need is the equation of that function. But to try to give this an intuitive appeal, I'm also going to draw the graph for you. What I want you to do is calculate the slope of the tangent line to this function that's pictured in red, whose equation is boxed up here, at this point where x equals 3. You don't need to actually draw that tangent line. Going forward, we won't even really consider the graphs and we won't need the tangent line. But just so you can tie this together, here's a picture of what we're doing. The first thing you need to know is to calculate the slope of the tangent line to f at x equals 3. What you will be asked is to calculate f prime of 3. It means the exact same thing. It's just in math, we usually don't like writing out sentences like this. We want to capture all the information in as much of a condensed form as possible. Calculate f prime of 3. Here's the general formula for doing that. It says that f prime of any number a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. It would be really easy to view this formula as just complete gibberish and not understand it at all. But I think it'll benefit you to think back that really it's just a simplification of this formula, and maybe this formula makes a lot of sense. We're just taking the limit of our average rates of change. To figure out the average rate of change, we need to know the difference in the y-coordinates divided by the difference in the x-coordinates. The way to think about the x-coordinates is they're 3 and 3 plus h, and 3 plus h minus 3 just leaves us with this h down here. I said I wasn't going to talk about the theory, and here I am talking about the theory. Let's calculate f prime of 3. Just using this formula that's written down here, f prime of 3 would be equal to the limit as h approaches 0 of f of 3 plus h, because in this formula we have the letter a, but what we want to calculate is a 3 in that place, so I'm going to change all the a's into 3's, minus f of 3 divided by h. Before we worry about any limits, let's figure out what f of 3 plus h and f of 3 are equal to. Well, that's easy enough. I have this equation up here for f of x, so if I wanted to know what f of 3 were equal to, all I'd have to do is copy exactly what I see written here, changing all the x's into 3's. I got 3 squared minus 4 times 3 plus 1. I got 9 minus 12 plus 1. I got negative 3 plus 1. I got negative 2. Oh yeah, that makes sense. F of 3 equals negative 2 because on this graph, when the input is 3, the output is negative 2. This point right here has coordinates 3, negative 2. What about f of 3 plus h? Well, if we don't worry too much about what this means, we can just go right back up to this formula and recognize that now our input is 3 plus h instead of x. So everywhere I see an x, I'm going to instead write a 3 plus h. So I would have 3 plus h squared minus 4 times 3 plus h plus 1. When I put 3 plus h into this machine, this expression is what comes out. This expression can be simplified, and it'll turn out it's beneficial to simplify this, so I'm going to go ahead and simplify it right now. 3 plus h squared, think 3 plus h times 3 plus h, think FOIL, you get 9 plus 6h plus h squared. To get rid of these parentheses, I take the negative 4 and distribute it through, and I get negative 12 minus 4h. And then I still have this plus 1 over here. If I combine like terms, I only have this h squared term, but if I look for my h terms, I got 6 of them here and negative 4 of them here. So that nets out to just 2 of these h's. And then if I look at my constant terms, I have 9 minus 12 plus 1. 9 minus 12 is negative 3 plus 1 leaves me with negative 2. When I put 3 plus h into this machine, a simplified version of the expression that comes out is h squared plus 2h minus 2. Now that I know f of 3 plus h and f of 3, I can come down here to my formula and put those in here respectively. I got h squared plus 2h minus 2 for f of 3 plus h, and from that I want to subtract f of 3, which is this negative 2. Be careful subtracting the negative here, and then I want to divide that by h. Before we ever considered limits, When this was just an average rate of change, we noticed that -2 plus 2 cancels out, so we just get h squared plus 2h up in the numerator and h down in the denominator. And conveniently, since every term in the numerator has an h in it, we can cancel an h from each of those terms with this h here, and we'd be left with just h plus 2. Note that this limit over here is really easy to calculate, right? The limit as h approaches 0 of h plus 2 is just equal to 0 plus 2, or 2. The reason why is h plus 2 as a function is continuous at the point where h equals 0. But this expression over here as a function is discontinuous at 0. So evaluating this limit is a lot more challenging than evaluating this limit. If you were to graph this as a function, and to be clear, this is not graphed as a function anywhere on this page, but if you were to graph this as a function with h as its input, this would have a removable discontinuity at 0. And what we're doing algebraically from this expression to this expression is we're filling in that hole to change this from a discontinuous function to a continuous function so that it's easy to evaluate the limit. But frankly, you, the student, don't need to follow any of that. What you need to know is, in order to evaluate this limit, I want to change all the h's into zeros. But I can't change all the h's into zeros right now because I'd be dividing by 0. So what I instead have to do is cancel out this h in the denominator, maybe that's a phrase you've heard before in this class, so that I can evaluate the limit. The limit equals 2. Because the limit as h approaches 0 of this expression equals 2, and this expression represents the slope of the tangent line to this function f at x equals 3, that tells us that the slope of this tangent line is equal to 2. I want to redo some similar calculations, maybe a little bit quicker, but before I do, I feel like I'd be cheating you if I didn't tell you one little thing here. This is the formula that we are going to use in our class to calculate the derivative. It's what's called the difference quotient. And if you can kind of see average rate of change in here, that's awesome. It's not the only formula that works to calculate the derivative. There's another one called the definition of the derivative, but it gives the exact same answer. Mathematically, it's identical to this formula. Here's the formula for the definition of the derivative. You can see some of the similar ideas in here, right? We have 2 different y coordinates and 2 different x coordinates. What's different down here is instead of considering the limit as h approaches 0 in order to get the 2 points that define the secant line to be equal to the tangent line, what I'm doing is considering 2 completely different points. One of them is b and one of them is a. And this second point b is going to get infinitely close to a. It's the same thing we're doing up here, but in order to get the 2 points close together, up here we say the difference between the 2 points gets close to 0, whereas down here we say the second point gets really close to the first point. Here the 2 points have x coordinates of a and b respectively. Here the 2 points have x coordinates of a and a plus h respectively. This one has a nice intuitive appeal to it, but algebraically, this one works out a little bit better. So this is the only one we're going to use in our class. Let's use this a few more times and then call this video good. What if I asked you to calculate f prime of 2? Be nice if you could look at this and understand that what you're being asked is to calculate the slope of the tangent line to this curve at the point where x equals 2, this point right here. Just looking at this curve, maybe you could tell me what that slope is. If you had to draw the tangent line to this curve at this point, what would it look like? If you're thinking about a horizontal line, that's perfect. That's exactly what it would look like. It'd be a horizontal line. And you're like, wait, don't horizontal lines just have slopes of 0? They sure do. Then shouldn't the slope of the tangent line to this curve at this point just be equal to 0? Absolutely. And let me show you algebraically how that works out. What we do is we take this formula right here. Playing the role of a would be the number 2. So we take the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by 2 plus h minus 2, which is the same as just h. And then we just have to figure out what comes out of our machine, which is defined up here, when we put 2 plus h into it, and what comes out of our machine when we put 2 into it. Well, let's see. I guess we'd get 2 plus h squared minus 4 times 2 plus h plus 1. I have this function memorized because I've used it so many times. That's the output when we put 2 plus h in. And when I put 2 into this machine, I get 4 minus 8 plus 1, which ends up being negative 3. And I want to divide that difference by h. Again, I get rid of all my parentheses. Over here, I have 4 plus 4h plus h squared. Over here, I have minus 8 minus 4h. I still have this plus 1, and then I have this plus 3. I want to divide that whole mess by h, and really what I should be doing is writing the limit as h approaches 0 in front of each one of these expressions, even though sometimes I get kind of lazy. This expression is going to simplify really nicely. Don't believe me? Well, let's see what we have. We combine like terms. We got this h squared term. If I look for my h terms, I got 4 of them here and negative 4 of them here. So those cancel out. And if I look at my constant terms, I have 4 plus 1 plus 3 gives me positive 8, minus 8 gives me 0. So up top, I just have an h squared. On the bottom, I have an h. I cancel one of these h's with one of these h's, and I get that my answer is the limit as h approaches 0 of h. Change all my h's into zeros. I get 0 as my answer, exactly what we thought it was going to be. If you want more practice with this, you can calculate f prime of 1 on your own. We don't need the graph for this. You should be able to do this completely algebraically, but I can tell you that 1 is this point right here on the graph. So the tangent line is going to look something like this as best as I can draw it. And you might notice some similarities between the red line and the blue line. Because of the symmetry of this graph, I think the slope of this tangent line is going to end up being -2. But I'll leave that as an exercise for you if you feel like doing it. However, before I end this video, I want to do this one more time. And it might seem like I'm beating this to death, but this question part D is going to be hugely important. So I really want to focus on this. Let's look at what it's asking us for. F prime of x. This is asking me for the slope of the tangent line to this function. Oh, really? Where do you want it to be? At x. I'm not even specifying the value. I'm not telling you that I want it at x equals 2 or x equals 3. I want it to be an expression. I want to leave the point at which we're calculating the tangent line unspecified. And you're like, whoa, that's getting really, really complicated. How would I draw that now? You can't draw it. I want to allow this x value to change and calculate the slopes of all these different tangent lines. Might seem really hard, but I think we have all the machinery necessary to do it. All we'd have to do is use this same formula. Playing the role of the a is no longer a 3 or a 2 or a 1. It's now the letter x. So to figure out f prime of x, we take the limit as h approaches 0 of f of not a plus h, but instead x plus h, minus not f of a, but f of x divided by h. Whoa, wait, can we do that? Absolutely. You figured out what came out of this machine when you put expressions like 3 plus h into it, so there's no reason we can't put expressions like x plus h into it. All I would do is copy exactly what I see here, except change all the x's into x plus h's. So I would get x plus h squared minus 4 times x plus h plus 1 as the output when I put x plus h in. From that, I would have to subtract. Here's some unnecessary parentheses to try to keep all these pieces straight in your head. F of x, which is what comes out of the machine when I put x into it, which is exactly what's written here, x squared minus 4x plus 1. I want to divide that huge mess by h. This is the limit I want to evaluate. And you're like, oh, this is going to be horrible to evaluate this limit. In order to evaluate this limit, I have to cancel out this h so I don't divide by 0. How in the world am I going to cancel out an h from this huge mess that's up top? The same way we did it before. Get rid of all the parentheses, combine like terms, and you'll see a really nice thing happens. Let's do it. X plus h squared. Think FOIL. X plus h times x plus h. You'd get x squared plus 2xh plus h squared. Then take this -4 and distribute it through the parentheses. You get -4x minus 4h. Be careful, make sure this is negative. Make sure it's the entire -4 you're distributing through, not just the 4. Then I have this plus 1. I'm now done with my first set of parentheses. I want to subtract my second set of parentheses. Take the implied -1 here and distribute it through the parentheses. Make sure the negative hits each of these 3 terms. So it becomes -x squared plus 4x minus 1. I've gotten rid of all the parentheses up top, and I just have an h left down in the bottom. It looks horrible. It looks like a disaster, but there's this nice built-in check. This h should be able to cancel out. In order for this h to cancel out, I better be able to get rid of all of my terms up in the numerator that don't have an h in them. Let's see if that happens. I got an x squared term right here, but I have a -x squared term right here, so those are going to cancel out. I have a -4x term right here, but I have a +4x term right here, so those are going to cancel out. I have a +1 right here, but I have a -1 right here, so those terms are going to cancel out. What does that leave me with up top? I have this h squared term, which definitely has an h in it. I have this plus 2xh term, which also has an h in it. And then I have this minus 4h term, which again has an h in it. I want to divide that by h. I cancel this h with an h from each of these three terms, and I get that this is the limit as h approaches 0 of h plus 2x minus 4. What is the limit as h approaches 0 of h plus 2x minus 4? Well, that's an easy limit to evaluate because all you got to do is change all the h's into zeros. Note, we could not change all the h's into zeros back in this step because we'd be dividing by 0. But by canceling out this h, we're able to evaluate the limit by changing all the h's into zeros, which is awesome. If all my h's are zeros here, this is just a 0, this stays 2x, this stays 4, and I get 2x minus 4 as my answer. F prime of x equals 2x minus 4. The power of this equation cannot be overstated. What this is saying is the slope of the tangent line to this function at any point x is just 2 times x minus 4. If I wanted to know what f prime of 3 were equal to, I could do it this way, or if I already knew f prime of x, all I'd have to do is say f prime of 3 is just 2 times 3 minus 4. It's 6 minus 4, it's 2, the same answer that I got up here. What about f prime of 1? Put 1 into this machine. 2 times 1 is 2. 2 minus 4 is negative 2. Here's that answer of negative 2 that we calculated before. F prime of 2 being equal to 0. Here's another way you can verify that. 2 times 2 is 4, minus 4 is 0. When you first learn about derivatives, you think about the derivative as the slope of the tangent line at a specified point to a curve. But really what we want to do is think about the derivative is a function in its own right. And that's the part that might kind of blow your mind. There's two different machines going on here. The first machine is this parabola pictured in red. This is a function, f of x equals x squared minus 4x plus 1. But there's another function, the derivative function, that is super powerful, and its equation is 2x minus 4. This machine takes x values as their inputs and outputs the slope of the tangent line to this function at that x coordinate. If I graph 2x minus 4, you might recognize that this is a linear equation. It fits the form y equals mx plus b. The y-intercept is negative 4, and the slope is 2. So it's this line that's poorly drawn in purple. The height of this graph in purple tells you the slope of the tangent line to the graph in red. And if that doesn't blow your mind, you are doing way better than I was when I was at this point in a calculus class. The height of this graph in purple at the point where x equals 3 is 2, right? The point 3, 2 is on this graph in purple. What does that mean? It means that if I were to draw the tangent line to the graph in red when x equals 3, like I did down here, the slope of that tangent line would be equal to 2. Where calculus gets super complicated is thinking about derivatives as functions. It'll take us a while to understand them, and the good news is we're going to kind of step away from that for a little while and focus on things a little bit more algebraically, but thinking about derivatives as functions will be kind of the key to understanding the first half of this class.